Introduction. This is a time where we are go to sleep because after having this nice meal, I can imagine that everybody feels like sleepy. So it doesn't matter if I speak English or if I speak Spanish. So no, because everybody is going to be sleeping. So today I'm here to talk about the one of our recent results regarding the consensus of robots. In this case, the consensus of Euler-Lagrange systems, because a robot can be modeled via the Euler-Lagrange dynamics or equations of motion. And today I'm going to talk about energy shaping in multi-robot systems. And what I'm going to show you are two solutions, one solution for the leaderless case and one solution for the leader-follower case regarding the consensus of the network. So I work with a team of colleagues at the University of Guadalajara who are Alma Lanis, Nancy Arana, Carlos Lopez, and myself. We together have a research group which is called Intelligent Systems. You are always welcome there in Guadalajara whenever you want to go. You are more than welcome. And internationally there are some people that I would like to acknowledge because the work that I'm doing cannot be possible without them. And they are Romeo Ortega, Professor Luis Bazañez, Yanis Sarras, Bayu, Gerardo Espinosa, and Marco Arteaga. So publicly I thank these people. The main part of the talk will be mainly based on these two research papers that they are just submitted. So what I'm going to talk about today is to achieve consensus of robots or Euler-Lagrange systems with interconnecting delays and without using velocity measurements. This will be the main part of the talk. However, there are certain things, there are a lot of things that I'm going to use also from these other three papers from 2011, 2013, and 2013. So this is the outline of the rest of my talk. First, I'm going to describe the scenario at which I work. Then I'm going to give you the fundamentals of the energy shaping controller. And then I'm going to provide the two solutions for the leaderless consensus and for the leader-follower consensus. Then I'm going to draw some remarks. I'm going to present some live simulations. I hope that they work. And then I'm not going to present some live experiments, just videos. And finally, I'm going to talk about what are the things that I'm currently doing and what are the future work for which I am interested in. So the word synchronization, the word consensus is a special case of synchronization, of a synchronization behavior. And the synchronization is the coordination of events that operate at the same time or at unison. So synchronization, we can find synchronization scenarios and applications everywhere. In nature, and especially in animal synchronization, we have them at flocking of birds, schooling of fish, flashing of fireflies, worker ants. But on other research fields, we have, as Professor Carlos Agüez presented us in the first talk today, we can encounter synchronization and consensus scenarios also in robots, in unmanned aerial vehicles. Moreover, we find synchronization on people. This is a really Mexican slide, a really Mexican photograph, because everybody here that has studied in the primary school and maybe in the secondary school, we all do honors to the flag every Sunday. So the people has to synchronize each other. We synchronize with the sun and with the night, so we go to sleep almost every day at the same time. And for people that have become a father or mother, sometimes wake up in the middle of the night and they are not synchronized anymore. And our coronary cells, they all pump together at the same time with the same rhythm, so we can live. And I'm going to show you a really interesting video for which we can see how synchronization works in nature. Maybe some of you have seen it before. And this is a really nice video because a basic form of synchronization. These are metronomes, and they of course are not synchronized at the beginning. They are interconnected rigidly through this wood, but now they have put some damping, and they have included an interconnection. In the interconnection they have included some damping that eliminates a tiny amount of energy that at the end we can see that they started desynchronized and then they went to a synchronized behavior. So they synchronize in phase and then frequency. And a nice thing here is that when they release the damping, then they are going to desynchronize again. What I want you to keep in mind with this video is that in order to obtain synchronization and consensus, we need interconnection. And such interconnection can be decentralized or centralized. As Carlos showed us before, I am also interested in behaviors that exhibit consensus and synchronization in a decentralized manner instead of a centralized manner. So, if I keep in mind that synchronization and consensus can occur when interconnection appears, then I would like to have a scenario where I can find different kinds of robots that work together, that maybe interact to perform a certain task together, that they collaborate, and they also collaborate with humans. In my PhD thesis, my work was mainly related to teleoperation systems, for which you have one robot interacted with a human, and then you have another robot maybe in another part of the world that interacts with a certain environment. And in that case, you have a small network of two robots. So after the PhD thesis, when I became a professor at the University of Guadalajara, I started to thinking, what else can I do? And then I thought, maybe there are a lot of things that one robot cannot perform. There are certain tasks that only one robot cannot perform. So what if I include more robots in the remote environment? Then I can perform different tasks that, unless I put more robots, one robot cannot ensure. So the things or the applications for which I am interested in are those where humans collaborate with robots, when you can find consensus and synchronization between different places. But in these kind of scenarios, besides the complexity of the collaboration of the remote robots, we also have time delays in the interconnection, because these robots can be located anywhere, and then you have another problem. So if you have different robots, interconnected them through a network, the interconnection then may exhibit time delays. So today I'm going to talk about how to solve these kind of issues using energy shaping controllers. And to do that, I have to model the interconnection, and I have to model the dynamics of each node, and I have to model everything. So I am considering a robot network composed of n, capital letter N robots, and every one of them is composed by small n degrees of freedom. I have to say that small n is the same for everybody. So that small n is the same degrees of freedom for all the robots in the network. Then I'm going to show you in a different slide that we have also worked with different synchronization scenarios where you can have different degrees of freedom for the robots. So I assume that the robots are fully actuated and they do not exhibit non-holonomic restrictions, which is a different scenario from the one that Professor Sagüez told us in the first talk. They have robots which exhibit non-holonomic restrictions, and the consensus solutions are different in that case. So in this talk, I am interested in this scenario, in this kind of systems. So the complete dynamics of the system is going to be described by two things: the interconnection of the nodes and the dynamical description of the nodes. At each node, I am going to assume that only one robot lives. So at each node, there is only one robot with n degrees of freedom that I'm going to model as an Euler-Lagrange system. So again, as we have listened before, in order to model the network, I'm going to use graph theory. And from graph theory, I'm going to borrow the Laplacian matrix. The Laplacian matrix is a really nice tool to analyze these kind of behaviors. And the Laplacian matrix is composed by a diagonal matrix, which is the weight matrix minus the adjacency matrix. But in this case, well, in the adjacency matrix, elements are these A sub ij. So the Laplacian matrix, this is the element ij of the Laplacian matrix, which is of size n. Recall that n capital letter is the number of robots. So the Laplacian matrix is a square matrix with n of size n. And from the adjacency matrix, if the robots are interconnected, then the item on the adjacency matrix is equal to 1, and if they are not, it's equal to 0. Actually, this can work also for a greater than 0. This is a special case of a graph which has all the weights equal to 1, but it can be a weighted graph. So we can have different weights in the interconnection. That doesn't matter here. It can be greater than 0 instead of 1. So this Laplacian matrix has also, this is just a reminder of the properties that we have listened before. All Laplacian matrices have a right eigenvector equal to 1, which is associated to the eigenvalue equal to 0. And this eigenvalue equal to 0 is unique if the graph is connected. So all the other eigenvalues, the real part is greater than 0. But I'm going to use an assumption here, and that assumption that I'm going to use here is that the graph is undirected. So this work deals only with undirected graphs. In that scenario, for undirected graphs, the Laplacian matrix is a symmetric matrix. And because it is a symmetric matrix, then the only one's eigenvector is a left eigenvector and also a right eigenvector, because it is symmetric. So these are the properties that I'm going to be using throughout my talk. And besides the first assumption that I just told you, I have another assumption that is regarding the interconnection of the robots. And I'm going to assume that the communication channel can exhibit time delays. But those time delays, although they can be variable, they are bounded. And the first derivative is also bounded. So I have two assumptions regarding the interconnection: undirected graphs and connected graphs, of course, and the communications can exhibit variable time delays, but they are bounded, and such bound has to be known. Okay? So for the nodes, as I told you before, I'm going to model them as a Euler-Lagrange system. So this is the equations of motion of the Euler-Lagrange And this is a really nice way to model the systems, because it relates the energy of the system. The Lagrangian is composed of the kinetic energy minus the potential energy of the system. So these are the equations of motion that can be written for each node in a short equation like this. This is really well known. This is a really well known equations in the robotics community for the people that perform control of robots. So this is a second order equation, non-linear. It has a really nice properties. And what I'm going to do is that instead of looking at each of the nodes, I'm going to look to all the network. So I'm going to put in a really big vector of size n capital letter times n small letter. I'm going to put all the positions, all the velocities, all the forces, and I'm going to create a couple of matrices that are block diagonal matrices. So I'm going to write, these are the description of each node, but I'm going to write this description into a really big equation, although it seems shorter because it does not contain the subindex I. This is a really big equation because it contains the description of all the nodes. So why am I going to do that? Because in this equation, if I give you the Hamiltonian function of the system, which is the total energy, which is really different from the Lagrangian is the kinetic minus the potential, so the total energy is the kinetic plus the potential. If I give you the total energy of the systems, which is the sum, the total kinetic is the sum of all the kinetic energies of the nodes, the potential energy is the sum of all the potential energies of the nodes. So if I give you this, then it is really easy to prove that this Euler-Lagrange system defines a passive map from the input force to the output velocity. Okay? And how can I prove that? If I use this as a Lyapunov candidate, then the time derivative along these trajectories is equal to this. This is a really nice property that we use a lot in robotics because the robot is passive. It's a passive system. So what I'm going to show you now are the solutions to two problems. The leader-follower consensus, where you have one leader position, and I have to recall that, well, I have to point out that this Q is a constant vector, so it is not a time-varying function, it's a constant vector. And what we would like to do is that for any initial condition, all the robots, we would like to converge asymptotically to this position and with zero velocity. And then I have the leaderless consensus at which we don't know where they are going to go, but we would like, actually it can be proved that it is in a convex hull of the initial conditions, but that is another thing. This position which I call the consensus position is a common position for all the robots. So what I would like to do is that from any initial condition, I want them to converge to a certain position that I call the consensus position. So in the energy shaping methodology, what we would like to do is basically that, to shape the energy. So we have that the agents have a Hamiltonian function, they have a natural energy, they have their own kinetic energy, their own potential energy, and what we would like to do is to incorporate a controller, which is a dynamic controller, that is going to change that energy. And we would like to design a desired total energy, for which that desired total energy is the energy of the system plus the energy of the controller. And we would like to design the controller in such a way that that energy has a global minima at our desired equilibrium point. And which is the most interesting thing or fact is that we would like also that equilibrium point, I will prove you that it will be global asymptotically stable. So the energy shaping methodology that has been known since the 1992 or 1991 by Professor Marquez Ponge and Professor Ortega, it's well known in the community, in the control community of robots. It's precisely that. They shape the energy of the complete system via the energy that can put or extract the controller. And this is precisely what I'm going to do. I'm going to design a dynamic controller that will have a controller energy. This is the total controller energy, which is also the kinetic energy of the controller and the potential energy of the controller. And if I do that, then I can find the Euler-Lagrange equations of motion of the controller, which are the equation number 3. So now I have two Euler-Lagrange systems living in the same node. I have the Euler-Lagrange system for the robot, and then I have the Euler-Lagrange system for the controller. And another interesting fact here is that if I design the energy as this and the dynamics of the controller as this, then that controller is a strictly passive map from input velocity to output the gradient of the potential energy of the controller. So this is really nice. Why? Because now you will see. if I had the desired energy as the total energy of the multirobot system plus the controller energy of the system, then the time derivative of this energy from fact 1 and fact 2 is equal to this equation here. Then it's obvious that if I design the controller in this way, this term will cancel this, it's going to cancel this term, and the time derivative of the desired energy is going to be negative semi-definite. So this is the energy shaping controller that achieves my desired objective. And if now the only trick and the only question is that, well, yeah, you can design a Euler-Lagrange controller. That controller can have the total energy, the energy of the controller plus the energy of the system. So now the question that arises is, how are you going to design the potential energy? And in the case of the kinetic energy of the controller, how are you going to design the inertia-like matrix? This M is an inertia-like matrix. So there are two questions: how to design M and how to design the potential energy. Because if I can give you the shape of the potential energy, then the controller is defined. Everything is defined. And I can use the desired energy as a Lyapunov candidate function. And now I have proven you that it is negative semi-definite. So it only rests to show you how am I going to design that energy in order to obtain the desired result. And for the leaderless consensus, the natural choice, and this is what is done mostly in the literature, is to cancel out the gravity. Mostly in robots, the potential energy is due to gravity. So I cancel out the potential energy due to gravity, and then I interconnect the controller and the system with a spring. And then I interconnect all the agents with a spring. And we know from classical mechanics that interconnecting with springs and a spring is a passive system that preserves power. So if I interconnect everything with springs and if I cancel out the energy, then I can design the potential energy of the controller as this equation here. This is the gravity cancellation. This is the interconnection with a spring of the controller and the system. And this is the interconnection with the springs also with all the agents. Recall that L is the Laplacian matrix. So if I do that, the desired energy has a global minimum in the position that I want, which is a consensus point, 0 for the velocity, the same consensus point for the position of the controller, and 0 for the velocity of the controller. And I am sorry to call position and velocity of the controller. I should have said the state of the controller. But it's analogous, the position and the velocities of the system and of the controller. So now, because I have given you the shape of the potential energy of the controller, then the controller is defined for all the agents. And this is the controller for agent I, which cancels out the potential energy and interconnects the plant and the controller, or the system and the controller, with a spring. So there's a problem, and our problem is that we have time delays. So if time delays arise in the communication, then the equation of the controller, the Euler-Lagrange equation of the controller, becomes this second order retarded differential equation which has a time delay which is time varying here. And this summation is nothing but the terms of the Laplacian matrix. So the main proposition is as follows. If you consider a multi-robot network with interconnection graph verifying assumptions A1 and A2, which is undirected graph, connected graph, and time varying delays but bounded and known, then if I give you the energy shaping controller that I just presented, and you set the damping gains and the proportional gains such as this inequality holds for any alpha sub I and alpha sub j positive, then we solve the leaderless consensus problem. The proof uses the total energy of the system, in this case is the desired energy of the system, for which after finding the time derivative and using it along the system trajectories, which becomes this inequality, then we can find and we can apply Barbalat's lemma, such as if we set the gain conditions, then we can ensure this. This implies that zeta dot belongs to L2 space, that the desired energy is bounded, the velocities are bounded, and then after applying Barbalat's lemma, I can prove my claim that the controller solves the leaderless consensus problem. So, in the leader-follower scenario, I have to assume another thing. I have to assume that the leader position arrives to at least one of the followers. It does not arrive to all the followers. It arrives to a given set of followers. In this case, it might be only one follower. And in that case, I can model the follower and the leader interconnection using this B matrix. And B is greater than 0 if that position is available to agent I. Is equal to 0 if it is not. So the controller design is basically the same, but now I have to include one more thing in the potential energy, because I want now to shape the energy such that the equilibrium point changes. Before, the equilibrium point was at consensus, and now I want the equilibrium point to be at the leader position. So I have to change the potential energy. If you change the potential energy and reshape it like this, then we can ensure that this equilibrium point is unique and is global. So if I use the desired energy as a Lyapunov candidate, and if I apply again Barbalat's lemma and everything, I can show you that this equilibrium point is globally asymptotically stable. So the controller in this case is the same for each robot, but the dynamics of the controller changes. Before, in the leaderless consensus, it doesn't have this term, because this term is the interconnection of the controller and the leader position. So before, we didn't have that term. So the main proposition for the leaderless consensus, for the leader-follower consensus, is that if the system verifies assumptions 1 through 3, then if gains are set such as the previous inequality holds, then the leader-follower consensus problem is solved. Again, the energy, the desired energy is the sum of all the energies. The time derivative is the same as in the leaderless consensus, and the proof follows the same steps as in the previous case. I'm going to give you some remarks. The energy shaping controller generalizes different controllers. In this case, I just gave you one controller, but now, because I have available, I can shape the potential energy. If I give you another potential energy, a different function as the potential energy, then a different controller will appear. So this scenario generalizes different kinds of controllers. There are actually, what I presented here is a family of controllers, and I give you one controller that can solve this problem. A nice thing here is that we don't require to measure the velocities. So the controller, in order to be implemented, we only require positions. And this is a nice fact, because before this is the first result in the literature that can deal with time delays, with consensus, and without relying on velocity measurements. So, of course, in the absence of delays, the interconnection of the robots is power preserving, because all the robots and all the controllers are interconnected through linear springs. And because I told you before, linear springs are power preserving, so the complete interconnection is power preserving. And if delays appear via damping, we can eliminate the extra energy generated. So I'm going to give you just a couple of simulations, live simulations. I hope they work. What you are going to see here are different results for different initial conditions. So in this case, I have a network. I should have shown you that the network is composed by 10 Euler-Lagrange systems. These are the interconnection weights between them, at each node, we have a 2 degrees of freedom nonlinear manipulator living there. So in that scenario, what you can see here is that these are the results for the 2 degrees of freedom for the case of a given initial condition. This is the case where that initial condition is minus 2, I believe. And the second initial condition, I don't know if you can see this, but the second initial condition is the original initial condition minus 2 for everything. And the third initial condition is the original initial condition multiplied by minus 1. So what I would like to see is how the initial conditions change in the leaderless scenario, the final consensus point. So in this case, look that for these initial conditions, this degree of freedom arrives almost to 2, and this degrees of freedom arrives to minus 2. But if I change the initial condition, then of course the consensus point changes. So what I'm telling you now is that the final consensus point in the leaderless consensus is affected by the initial conditions, but not only by that, but also because we have time delays, but it's affected with the time delays. Unfortunately, because I don't have the mathematical tools to prove it, this is only shown in simulations. Because I have a nonlinear system, the Laplace transform does not exist, and what people do in robotics and in other fields in order to prove the convergence point in the leaderless consensus is to invoke the final value theorem, at which we have to invoke the Laplace transform, and we don't have Laplace transform here, so I cannot prove it for nonlinear systems. And what I'm going to do now is that I'm going to interconnect the network with the leader. So A, in this case, is the leader-follower interconnection. The leader-follower interconnection, the leader is only connected to one of the robots. The leader desired position is minus 2, 3. And what I would like to see is that independently of the initial conditions, at the end, the final consensus point is the leader position. So recall that the leader in this simulation only arrives to one of the nodes. So this is everything for the simulations. And what I would like to show you now are some experiments. We have applied these results with different robots. Even though this is a 6 degrees of freedom and this is a 7 degrees of freedom, this is a KUKA lightweight robot and this is a Stovely TX90 robot, even though they have different degrees of freedom, one of the degrees of freedom here is stuck. We're not moving 1 degree of freedom. So this is why we can see these kind of results. This is a network with 3 different robots. Of course, the robots are in the same laboratory here, so the question arises, there are no time delays there, because everything is in a scenario where the communications, the delays are almost negligible. So, we have performed some experiments from Guadalajara. This is the laboratory in Guadalajara, and this robot is located in Barcelona. So these robots are interconnected through the internet, and they are synchronized because they are at consensus. As I told you before, these results, the consensus results for multi-robot systems, came from the question, if we have a teleoperation system which is composed by 2 robots, maybe we can extend all those results to a bunch of robots. So this is an old video. It was when Professor Spong was working at the University of Illinois, so it was in 2007, but I presented it here because the energy shaping controller is a generalization of the controllers that I did also, that I designed in my PhD thesis. And this video, although it is an old video, is still viable under the fact that those results are incorporated in the new energy shaping methodology. So this robot is been moving, and we can feel the interactions from Urbana Champaign and Barcelona. So what are the things that we are currently doing and we are currently solving? So we are solving and we are aiming at solving the consensus of multi-robot systems with non-holonomic restrictions. We are porting the notions of energy shaping controller to finite time regulation problems in robots. So we would like to design algorithms in such a way that we can establish a finite time property, convergence property. We are extending the consensus results using this methodology, the energy shaping methodology, in order to have synchronization and consensus in the special Euclidean space of dimension 3, at which we can have robots with different degrees of freedom, and because all the robots and everybody interacts in this space, then we can synchronize and we can find consensus solutions in that special Euclidean space. So those are the things that we are currently doing. What we would like to do in the future, we would like to extend these results to under-actuated Euler-Lagrange systems. We would like to include a larger class of agent dynamics like Hamiltonian dynamics, because Euler-Lagrange can model a different wide range of systems that includes the robots, but the Hamiltonian can model even chemical processes and a lot of systems. So we would like also to analyze topologies that are time varying. In this scenario, what I presented here is that the Laplacian matrix is a constant matrix. The Laplacian matrix relates the interconnection of all the agents. We would like to see what happens when that Laplacian is time varying, when the interconnection changes. What happens if in a mobile robot scenario, one of the robots loses the Wi-Fi interconnection? What happens then? All the robots are going to stay at the same place. All the robots, what are going to do the other robots? What is going to happen in that scenario? And we will also like to include directed graphs. The inclusion of directed graphs is more of a theoretical result, because we know that if we have one-way communications via Wi-Fi, then we can have bilateral communications. Once you establish one communication in one way, then it's really easy to establish the communication both ways. But it is a really nice theoretical solution to include directed graphs. So this is an academic resource that I would like to do. If anyone is interested in more details, I will be very happy to show you more details and to expand the proof, to extend the proof. I would like to thank your attention. I would like to thank the organizers of the workshop, especially to Hector. You are all very kind. I would like to thank you all for not sleeping. I have seen some faces that were sleeping, but most of you were not sleeping, so thank you for not sleep. And I'm open to questions. Thank you. Thank you.